So let's use our rational roots theorem and our synthetic division to find all the roots, all the zeros of this polynomial function. First, we're going to look for the leading coefficient and the constant. The constant is -2 and has the factors plus or minus 1, plus or minus 2. The leading coefficient, fortunately, is 1. So all these divided by 1 doesn't change a thing. So for our synthetic division, we need to decide to take any of these numbers, and I've already tried some of them, so my suggestion is let's start with the number 2. Divide our polynomial by 2, put in our coefficients, 1, -6, 9, and -2. Bring down the 1. 2 times 1 is 2. -6 plus 2 is -4. 2 times -4 is -8. 9 plus -8 is 1. 2 times 1 is 2. -2 plus 2 is 0. And guess what? This worked. So that tells us that 2 is 0. So we can write down our partially factored function. F of x is equal to x minus 2 times, now let's use our coefficients here from the result of our synthetic division, and starting off with a cubic function, we now have a quadratic function, 1x squared minus 4x plus 1. And this is the part that we now need to continue to find solutions for. In other words, we're saying we need x squared minus 4x plus 1 to be equal to 0. Looking at our target sum and our target product, we realize that we can actually not factor this particular function. We could use the quadratic formula or completing the squares. In this case, I suggest we go ahead and use the quadratic formula. We get x has to be equal to 4, the opposite of b, right? Plus or minus the square root of -4 squared minus 4 times 1 times 1 all over 2a, which is 2 times 1. Then we get x is equal to 4 plus or minus the square root of 12 divided by 2. Now we can do something with the square root of 12. So go ahead and do that in your margin to the left. The square root of 12 can be broken down into 3 and 4, right? And the square root of 4 is 2. So we actually get 2 times the square root of 3. In other words, we have x is equal to 4 plus or minus 2 times the square root of 3 all over 2. And guess what? Since all these three numbers can be divided by 2, we can simplify, and we get 2 plus the square root, 2 plus or minus, the square root of 3, and now have all of our zeros, which are x is equal to 2 is equal to 2 plus the square root of 3, or equal to 2 minus the square root of 3. Make a nice circle around it, and here's our answer. Remember, our rational roots theorem tells us that if we have rational roots, then they will be a number from those numbers that we got up there, plus or minus 1 and plus or minus 2. But we can, and very often also, have roots that are not rational roots, and those we obviously can't find that way. Those we can only find by using some of the other methods that we have learned before. Let's go to our next example, and this one is a little bit more involved as we have a quintic function. So, but let's not get scared. Let's just start doing what we always do. We need to find the factors of negative 14 and the factors of 1. Again, fortunately, the leading coefficient is positive 1, so not too much to worry about there. And in terms of factors, we got positive negative 1, positive negative 2, positive negative 7, and positive or negative 14. Those are our possibilities. I have a hunch that for our synthetic division we should start off with a negative 1. Wink wink. Right? So let's set up our synthetic division. Our box needs to be a little bit bigger this time. And our coefficients in here are 1, negative 4, 4, 10, negative 13, and negative 14. Even bigger than that. Alright, bring down our 1. Negative 1 times 1 is negative 1. Negative 4 plus negative 1 is negative 5. Negative 1 times negative 5 is positive 5. 4 plus 5 is 9. Negative 1 times 9 is negative 9. 10 plus negative 9 is 1. Negative 1 times 1 is negative 1. Negative 13 plus negative 1 is negative 14. Negative 1 times negative 14 is positive 14. Negative 14 plus 14 is 0. And yes, we are in luck. Negative 1 is one of our factors. And we have now turned our quintic function into a quartic function. Let's just write that down and keep track of it. We still need to keep going with our synthetic division to peel off more layers from our original quintic function. I'm going to suggest for the next step, we're going to use the next number in our list, positive 2. And we're going to go bring down our 1. 2 times 1 is 2. Negative 5 plus 2 is negative 3. 2 times negative 3 is negative 6. 9 plus negative 6 is 3. 2 times 3 is 6. 1 plus 6 is 7. 2 times 7 is 14. Negative 14 plus 14 is 0. And yes, 2 worked indeed as another 0. And we now have turned this into a cubic function. And we need to continue with our synthetic division. But here is one thing we can do in order to determine what number to use next. We have a cubic function now, and the cubic function of the form x cubed minus 3x squared plus 3x plus 7. And we can also use our calculator to help us out a little bit and see what could be a possible 0 of this cubic function. So let's take our calculator. I already plugged the function in here in y is equal to, and let's look at the graph. And when we look at the graph, we see that this function seems to have a 0 at negative 1. Another one at negative 1. All right. Well, let's use this knowledge for our next step of the synthetic division. Bring down the 1. Negative 1 times 1 is negative 1. Negative 3 plus negative 1 is negative 4. Negative 1 times negative 4 is 4. 3 plus 4 is 7. Negative 1 times 7 is negative 7. 7 plus negative 7 is 0. Yes, it did work indeed. And now we have finally peeled down our function into a quadratic function. Let's summarize what we have so far in terms of solutions. We have f of x is equal to x plus 1. And we actually have that twice, right? Negative 1 worked twice, so we can square this. Then we got x minus 2. And our quadratic function that we have left at this point is x squared minus 4x plus 7. X squared minus 4x plus 7 has to be equal to 0. And again, we'll find that this function cannot be factored. But since we got our b being an even number, we are going to go ahead and use completing the square this time. X squared minus 4x. Moving the 7 to the other side, and we have room now for half of the negative 4 squared, which is positive 4. On the opposite side, we have negative 7 plus 4. We have x minus 2 squared is equal to negative 3. And now we're going to take the square root of that. X minus 2 is equal to plus or minus the square root of negative 3. We know that the square root of negative 3, we need to take an I out. So moving over here, x minus 2 is equal to plus or minus I times the square root of 3. Now we add the 2 to both sides, and x is equal to 2 plus or minus I times the square root of 3. So for all our final solutions here, final zeros, we got x is equal to negative 1, which is a double root. Remember double roots. 2 and 2 plus I times the square root of 3, and 2 minus I times the square root of 3. Those are our zeros, and that's that. And if we think back to our fundamental theorem of algebra, looking at a degree, we say we have to have 5 solutions, and now we only have 4 numbers, but one of them, negative 1, is a double root. So that counts for 2, and therefore we do have 5 solutions. Let's move on to a couple of other theorems which are very important for us to know and use. The irrational conjugates and complex conjugates theorem. So the complex conjugates theorem states that if a plus bi is a root of a polynomial, then a minus bi must also be a root of that polynomial. And the irrational conjugates theorem states that if a plus the square root of b is a root, then a minus the square root of b must also be a root of that same polynomial. Essentially, what these two theorems are saying is that irrational roots and complex roots always come in pairs. It's because of the plus and minus sign we have in the number. Those always come in pairs. So we can use this knowledge to answer the next question. If 2i and 1 minus the square root of 3 are zeros of a polynomial, what numbers must also be zeros? And what does that mean? What is the minimum degree of this polynomial? Well, if 2i is a zero, then following the complex conjugates theorem, negative 2i also has to be a zero. And if 1 minus the square root of 3 is a zero, then 1 plus the square root of 3 is also a 0. So we have 4 roots we already know about. So therefore that polynomial must have at least a degree of 4. At least means that the degree could be higher. We don't know that, but we know, since we already found 4 solutions, the degree has to be at least 4. So how can we write equations of a polynomial if we have given the roots? Write a polynomial of least degree. Again, least means that that's all we can say at this point, maybe larger, but it needs to be the least degree that has a rational coefficients, a leading coefficient of 1, and zeros at 2, and 2 minus the square root of 5. And if we have zeros at 2, that means one of our factors is x minus 2, and we have another 0 of 2 minus the square root of 5. We know that 2 plus the square root of 5 also has to be one of our solutions. For a rational solution, we can find the factor fairly easily. For our irrational solutions, it doesn't quite work as nicely, so we need to remember the technique of uncompleting the square in order to find the polynomial, the function. If x is equal to 2 plus or minus the square root of 5, then we move all the rational parts to one side. X minus 2 is equal to plus or minus the square root of 5. And now we can go ahead and square both sides. When we square the left and we FOIL it, we get x squared minus 4x plus 4. And on the right, we get 5. No more plus or minus, because squares always have to be positive. Move the 5 to the other side, so we get equal to 0. X squared minus 4x minus 1 is equal to 0. And now, based on this, we can write our final function. F of x is equal to x minus 2 times x squared minus 4x minus 1, all in parentheses. Let's try one more example where the information we are given is a little different. Write the equation of a polynomial with zeros at negative 4, 1, and 2, and with a y-intercept of 0 and negative 6. Well, we can write down the function already based on our zeros. We have x plus 4, x minus 1, and x minus 2 as our factors. But we also have a dilation. The dilation at this point we just don't know yet. So I'm going to plug in a for a dilation, and this is what we need to find. Well, let's look at the other piece of information that we had. We were told that this function has a y-intercept at 0 and negative 6. So we are saying that if we plug in 0 for x, everywhere we have an x, then the outcome, the output, will be negative 6. So let's write this down. Negative 6 is equal to a times 0 plus 4 times 0 minus 1 times 0 minus 2. And if we do the math, we get negative 6 is equal to a times 8. Well, let's divide by 8. Negative 6 over 8 is equal to a, which we can simplify. Negative 3 over 4. And now we can go ahead and write our final function. F of x is equal to negative 3 over 4 times x plus 4 times x minus 1 times x minus 2. This is the function that we have written based on the given information. That's it for today, and I will see you in class.